As with any proof, the questions we have here now are going to revolve around trying to show that a given statement is true. However, what's different about proof by contradiction is the specific format we're going to use when doing so. For here, not only are we just going to show whatever the statement is straightforwardly, no, here we need to try to show the opposite and fail, therefore meaning that the actual original statement must be true by contrast. So, if we were to have a statement such as this, we have if x is odd, then x cubed plus 1 is even. If we were to prove this by contradiction, we must first of all give a contradictory statement. That would be that if x is odd, x cubed plus 1 is also odd, so keeping the rest as was. Now then, we need to try to show that that is indeed odd and then fail doing so. To start off with, we therefore need to create an alternative expression for x which has to be odd. In general, if you need to create an even number, you would use 2n, because whatever n is, because it's being times by 2, that has to now make it even. An odd number, therefore, is 2n plus 1. It's not good enough to just have n or n plus 1, because in that case that still could be any number. But because it's 2n, which has to be even, 2n plus 1, one more than even number, has to be an odd number. This expression here is guaranteed odd. Now then, if we were to cube this, if this is our x, x cubed is going to be 2n plus 1 cubed. So you can think of that, if you like, as this squared, then times by another one of itself. So 2n plus 1 squared would be 4n squared plus 4n plus 1. So this then gets times by another 2n plus 1 to give 8n cubed plus 12n plus 6n plus 1. Now don't forget that once we have this x cubed, we need to add 1 to it. So we in essence have 8n cubed plus 12n plus 6n plus 2, because 1 over 1 is 2. With this, what we can do is we can factorize out a factor of 2 to leave us with 4n cubed plus 6n plus 3n plus 1. Now, because it has a factor of 2, it is therefore not odd. Therefore, we have a contradiction. And if we have a contradiction, then we know that the original statement was true. Similarly here, if we're going to have there are no integer solutions to 3a plus 6b equals 1. Well, here immediately you might think, well, are we going to have to test every single integer possible value? No, even though we have two unknowns, we're not just going to be randomly putting in any kind of numbers trying to find something. What we're going to do is we're going to try to simplify first to, well, kind of like we did here, take out a common factor. Here, the common factor would be 3. So if we were to take out 3, we'd be left with a plus 2b equals 1. And so just dividing by that, a plus 2b equals a third. Okay, so we've made this rewriting. Well, what's the significance of that? Well, the significance is that the contradictory statement to this would be that there are integer solutions. Integer, again, just to clarify, meaning a whole number. Well, if we now look here, if we're saying there are integer solutions, they're saying there are whole numbers for both a and b for which this works. A here then is a whole number, and 2b will also be a whole number because it's an integer times an integer. And yet this is now equal to a fraction. So what we can say is the sum of integers cannot equal a fraction. Therefore, it's a contradiction. and therefore the original was true. There are no solutions. With these kind of proof by contradiction questions, they can throw at you slightly different formats. So maybe it was a squared, or maybe it was plus something else. Or here, maybe the different numbers in front here. Even so, we're still going to be working around similar premises. Other kinds of proof by contradiction questions, however, are going to be even more of the same as each other. For instance here, the root of 5 is irrational. There are various square roots are irrational, surds are irrational questions. The number underneath is going to be different, but the methodology will be the exact same. First of all, we should just clarify what our contradictory statement would be. So that would be the root 5 is rational. And then before we get into the method, another thing to clarify, what does that even mean? What does it mean if something is irrational or rational? Well, if x is rational, then x equals a over b, where a and b are co-prime integers. Now, what co-prime means is that they don't share a factor. Okay, so we're trying to show if something is rational, you can express it as two whole numbers divided by each other, where they then don't have a common factor. So if it can't be expressed as this, then it should be irrational. With that in mind then, how we're going to start off a bit of working like this is say, okay, if root 5 is rational, then root 5 is going to equal this a over b. Therefore 5 will equal a squared over b squared. Therefore 5b squared will equal a squared. From this statement we can say that a squared is a multiple of 5. And if a squared is a multiple of 5, then a on its own is also a multiple of 5. You can't have a square number in a given times table if the regular number isn't also in that times table. With that in mind, if a is a multiple of 5, then we can say that a is like 5c, or whatever other new letter you want to introduce. It's 5 times something else. Given that a has this value, we can then take this back over to that expression and say that 5b squared equals 5c all squared. So 5b squared equals 25c squared. Therefore, b squared equals 5c squared. With the same logic, we can therefore say that b squared is a multiple of 5 and that b on its own is a multiple of 5. But if both a and b are multiples of 5, that means that a and b are not coprime. Therefore, we have found our contradiction. Therefore, the root of 5 is indeed irrational. Regardless of what number they put under the square root, so long as it's a surd, this would be the exact same working that you would do, it's just this 5 would change for whatever number that is there. Still on the topic of rational and irrational, we have the sum of a rational and an irrational number is irrational. Well, the contradiction of this would be that it is rational. Therefore, if we would say, okay, a rational number would be a over b, and irrational couldn't be expressed as this, so it would just be c. If the sum of this was then rational itself, we could say that that is in turn some other fraction of coprime integers. So both a and b are coprime integers with each other, and d and e are coprime integers with each other. Trying to rearrange for c, you'd get c equals d over e minus a over b. To minus these fractions, you need the same denominator, so we'll make it both over eb, but in order to do that, d gets times by b, and then minus a times e. Now this fraction here is just a load of letters just next to each other, but the important thing is that all of these letters are integers. And if you have these integers, times together is going to make an integer, minus another integer expression here, divided by another integer expression here. Integers divided by integers, and we can see here this is not going to share a factor with this because there's no common letter that you can cancel everything through by. They are co-prime integers. That makes this here rational, but we've already determined that this c is irrational. So what this gives us here is that irrational equals rational, which can't happen. Therefore, we have our contradiction. Lastly, the third kind of proof by contradiction you might have is to show that there is no largest something or other. So for instance here, there are infinite prime numbers. Well, the contradiction to this, there would be finite prime numbers, and that is, there is a largest prime number. Now, proof to contradict this would be that, okay, let's say there's P, where P is the product of all primes. What does it mean then if we have P plus 1? Well, there's two options for what P plus 1 could be like. Either it has prime factors. That is, we could divide it by some prime numbers. If this has prime factors, these have to be different prime factors to P because they cannot share factors because they're consecutive. If you have two numbers next to each other, they can't be divisible by the same thing unless it's like just 1 and 2. But if it has prime factors that aren't factors of P, yet P is supposed to be all prime factors, it meant to be all of the prime numbers times together, this would mean P is not all primes. Alternatively, we could say that P plus 1 has no prime factors. That would make P plus 1 itself prime. And if P plus 1 is prime, and P plus 1 is obviously greater than P cannot be the product of all primes. So again, we get back to this conclusion that P is not all primes. Therefore, in either case, P does not fit its own definition. P cannot exist. Therefore, we have a contradiction. There cannot be a greatest P, or greatest prime, because you shouldn't be able to times all of the prime numbers together. Lastly then, just also bridging back to what was on the previous screen, there is no largest positive rational integer. Well, the contradiction to this would be that there is a largest. That we could have some rational numbers, let's say R, for which there are no bigger rational integers. So R is the largest. What then happens if we have R plus 1? Well, given that R is rational, we can express this as an A over B plus 1. To try to combine these together as a single fraction, we would need a common denominator, so the 1 can instead be expressed as B over B, because anything over itself has a value of 1. And now we have the same denominator, you can combine that together as A plus B over B. Because A and B we know are integers themselves, and now the numerator and denominator are co-primes because you can't cancel through by a common factor in its entirety, this itself must be rational. So the number above R is rational, therefore R is not the largest positive rational number, and thus we have our final contradiction here. As I've said, while the questions can kind of mix up the exact numbers or wording, a lot of proof by contradiction is just going to follow one of these 6 models here. So long as you're happy with the different proofs that we can use and just apply them to a given situation, understanding that that is which one, whatever it's calling for, you should be okay, especially with like the prime numbers one. There's only really one thing you can do with prime numbers, which would be that they are infinite. So you would just parrot back this explanation here. As such, there aren't any other practice questions in this video. What I'd suggest is what you could do is just potentially make up some questions of your own or find some online and just try to implement whichever method makes sense to it.